Morning, good afternoon, wherever you may be in this day. Thank you, as always, for choosing to make chemistry part of your day. All right, so we're going to continue with light. We're going to talk about energy. We're going to lead into quantum mechanics, and we're going to lead into electrons and orbitals in actual chemistry class. So there we go. First of all, I'm going to try to explain a few things here. What I'll actually test you on is probably rather limited, but I do want to explain some concepts here. So first thing is, here's a fancy tube with hydrogen gas in it. You can tell this has got H2 there. And if we excite it, we add energy, heat it up, put electricity in, whatever. What we'll see is, and if we were to take the light that comes off of that and put it through a prism, where you know those glasses, you can look at a Christmas tree and it makes little funny shapes and spreads it out. So same kind of idea. If we were to do that with hydrogen gas, and look at the light that comes off it, what we'll notice, which is kind of surprising if you really think about it, is we only get a couple colors of light. We'll see a bright red line, which if you wanted to quantify is at 656 nanometers. We'll see a pretty green line at 486 nanometers. We'll see a strong blue line at 434 nanometers, and we'll see a purple line at 410 nanometers. But what's the interesting part is what we don't see. We don't see anything here. We don't see anything here, here, or here. We're not seeing the rainbow. We're not seeing all the colors. And we're not seeing all the energy. So each of these colors corresponds to a specific energy. So we're seeing something that is not continuous. And the fancy word for not continuous, only certain allowed values are allowed, is quantum. So this is quantized data or quantum data, and sometimes these words are scary. We get into quantum mechanics and things that sound like the math and engineering is daunting, and it can be. But the idea of quantum is super simple. If I go to the market and I ask for 2.73 cans of Dr. Pepper, what's going to happen? They're going to look at me funny, and they're not going to sell me 2.73 cans of Dr. Pepper. You know why? Because I can buy 2 cans of Dr. Pepper. I can buy 3 cans of Dr. Pepper. If I told you right now I had 1.8 markers in my hand, you'd call me a liar. Now I can have 3 markers. I can have 2 markers. I can have 1 markers. I can have no markers. If you get that idea, you understand quantized data. Only certain values are allowed. Typically, we'll multiply weird numbers by a constant so that we can do things literally like 1, 2, 3, 4, 5, 6 are your allowed states, or -1, -2, -3. So they're nice whole number representations. So that's the idea of quantized data. It really just means not continuous, only certain allowed states. So okay, we covered quantum. We only see certain colors come out of hydrogen. And if we do the opposite, this will happen too. If we take hydrogen, if we take bright light, if we take continuous light, and we shine it through a tube of hydrogen, we'll actually see black spots appear at these exact same points where the it's disappearing. So what's going on here at the chemistry standpoint? So a couple concepts. Number one is we're going to assume that, again, chemistry is the study of electrons, the energy levels, what's changing, what's moving around is the electron. So with that assumption that we're talking about electron energy levels, we can't have all levels. There's only certain allowed levels. That's what this data tells me. The other piece of interesting information here is that they're not equally spaced either. And this result wouldn't show this, but we do know at this point that it's kind of a harmonic. They get closer and closer together as we go up. So there's 2 things I want you to get. The electron can only be in certain places, and that these levels get closer together as we go. The further an arrow is on the board, the more energy it has. The shorter an arrow is on the board, the less energy. Low energy is at the bottom of the board always. High energy is at the top of the board always. And things tend to go to their low energy state. If I let you run around every day, I hope you come to your low energy state. What do you do every day? At some point you do what? You get to your low energy state, which we call the ground state. And then in the morning, you wake up, you grab your cup of coffee, you get excited to work chemistry problems, and you are in a very high excited state. And then you finish your chemistry problems, you lose a little energy. You go to another class, maybe you lose a little more energy, hopefully you get energy. And then at the end of the day, you do what? You go back to that ground state. Electrons do the same thing. We can put energy in, they get excited, but at some point they're going to go back to the ground state. And they can do this lots of ways. They can do this in a whole series of steps, and do this in one huge step. And all these different combinations are possible. And so I actually put up the real data for hydrogen. Going from the 3-state to the 2 states of our red line, the next one's the green, the blue, the purple. If it's shorter, if it was from here to here, this would be too low in energy. It would be infrared. We wouldn't be able to see it with our eyes. This is too large an energy gap. This would be ultraviolet. We wouldn't be able to see that with our eyes either. So we only see a very limited part of the spectrum. And I probably should have talked about this in the slide on the last one. We have all that stuff from gamma rays all the way down to radio waves. We see just a really little narrow sliver, and I didn't even talk about this, but we see from about 350 nanometers. Everybody's eyes and genetics are slightly different. But somewhere from 350 nanometers up to somewhere around 700 nanometers. Again, everyone's eyes are a little bit different. Where you see the end of red on the rainbow, somebody else might see a little more, a little less, and so this cutoff, I'm going to use 350 to 700 as our visible spectrum. If you want to use 300 to 800, depends on your eyesight. So, and then after that we get to ultraviolet, and over here we get to infrared. And then you get the whole Roy G. Biv, going from high to low wavelength or low to high energy. Okay, so when we excite the electron, we put energy in. This is called absorption. We're absorbing the energy. When it comes back down to the ground state, this is emission. This is the basis for almost all testing we do in science, or at least chemistry, probably a lot of physics, and a lot of your other disciplines as well. This idea of excite and emit. And we can either look at what disappears from an absorption spectrum data, or we can look at what appears from an from an emission standpoint. And that's really what we call, this is the basis of all spectroscopy. And this is the basis for a lot of the analysis we do. Particularly if you're looking at elemental analysis, metals, so if you're looking at, is there any copper in your water, those kind of things. Mercury, maybe not mercury, but lead in your water, things like that, we do this. And there's lots of different methods for doing this and methodologies, but this is really the basis for a lot of analysis in the quote-unquote real world, in a real lab. A little bit beyond the scope of what we get into in Chem 101, we got to walk before we run, but just to let you know, there's a lot of really good science, practical science explained with this graph. And then we just look at what disappears, we look at what appears, and that's our analysis method. Speaking of which, I forgot one key point. Every single element has a different set of lines. So it's like a fingerprint, if you will, for the elements. So if you ever wonder how we can say what the atmosphere on some moon of Jupiter is, we can look at where these black lines are going, from the light coming behind the moon to Earth. And we can determine pretty well what elements are in the atmosphere there. So just to let you know on that. So these are really like a fingerprint. Every element's going to have its own unique fingerprint. And if you can find a line that only shows up from one element, it's awesome. You can just look at one place and you can determine the amount of that compound. I'm going to do this rapidly. I know you don't believe me. Historically, Planck around 1900 started to find that heating up metals and looking at the light that comes off it was quantized. And this relationship was found. Einstein, what he actually got the Nobel Prize for was the photoelectric effect. It wasn't relativity. And it was in 1905. And without really going into the experiment too much, he shined increasingly more energetic light at a metal, and he saw how many electrons came off it. And what he basically saw is 0 would come off until a certain point was hit. And then the same amount would come off no matter how much energy he used. But if he used twice as much light, he could get twice as many electrons off. This was the basis for saying that light is not just a wave. It is also a particle. So light is behaving as both a particle. We've already talked about the wave-like properties of light. So it's both a particle and a wave. And these particles are called photons. And if you want to think a photon is kind of like an atom, it's just an atom is just the smallest itty bit of material. And a photon is the smallest itty bit of light or electromagnetic radiation. You're absolutely correct. You got the right idea. Mathematically, let's put this all together. If energy is now related to h, which is Planck's constant, 6.626 times 10 to the minus 34. Again, don't memorize it. Find it from Bob, back of the book, back page of the test. I'll give you constants. There's Planck's constant. times the frequency, which is the same frequency we used before. We can combine these two, the equation from earlier, speed of light equals frequency times wavelength, do a little math the magics and move the wavelength over, plug that in, and we get E equals hc over lambda. And we now have a relationship to relate any two of our three properties of light. And just like before, frequency is 1 over seconds, wavelength is meters, energy is always, when we use this, going to be joules over photon. So, what does that look like? I'm glad you asked. Calculate the energy of a photon of blue light. So, again, energy, a length. So I want the relationship between energy and wavelength. So luckily I've memorized this, and I know this is my relationship. So Planck's constant is just a constant. Speed of light is a constant. And my wavelength, again, I need to convert that. To try to keep this video short, I'll divide by 1,000,000,000 right now in my head. And we get this. Now we can plug this through. And this I cannot do without a calculator. And I get my energy as 4.3 times 10 to the minus 19 joules per photon. Okay. That's a joule of energy. This is 0.000000000000000000004 of this. Doesn't seem like enough energy to do much of anything, and yet somehow blue light can make reactions go. We have things like photosynthesis. We worry about UV light changing the chemistry of my skin and giving me cancer. Scrambling my DNA. What am I missing? You know what you're missing? We're still in physics class. Don't tell Dr. Wargo, he thinks it's chemistry. But we're going to make it look like chemistry. And thinking back to that whole series of videos we had in enthalpy, all those things are kilojoules per mole, like 100. You need like 100 kilojoules per mole to move a bond around, right? So what would that look like in kilojoules per mole? Well, let's do the easy part. 1,000 joules is a kilojoule. Boy, that didn't help us. Now we're going the wrong direction. But what's a mole? A mole is 6.02 times 10 to the 23rd anythings. In this case, my anything is photons. So now, I get a number that's 260 kilojoules per mole. I feel much better because we've moved from physics class to chemistry class. And that makes sense. I can rearrange a lot of chemical bonds with 260 kilojoules per mole. That is something I can work with from a chemistry standpoint. So just remember, when you use this equation, E is going to be joule per photon. So sometimes we can work the other way, right? The problem says you need 260 kilojoules per mole to initiate a reaction, calculate the minimum wavelength of light. You'd have to then take this kilojoules per mole and do the opposite calculation. But I know you guys are awesome at the railroad track, so this isn't going to be an issue, right? A mole is 6 times 10 to the 23rd. A kilojoule is a joule. And that's what we'd plug in here. And you'd solve for your wavelength, which would be in meters, and you convert to nanometers using the railroad tracks and the metric system again. So hopefully you're getting good at those things. Quickly, I'll try to do this in a minute or less. De Broglie basically said, well, if we know light's a particle and a wave, can everything be a particle and a wave? Do a little mathematics, you get the de Broglie relationship. Wavelength is Planck's constant over the mass in kilograms times the velocity in meters per second. So if I take the fastest baseball thrown in Major League Baseball history, and I calculate the wavelength that we expect, if it's both a particle and a wave, it would have a wavelength of 1.2 times 10 to the minus 34. Undetectable by all methods. I hate to use the word never, but I'm not convinced we will ever have ability to detect something so small, so this is hypothetical. But what if these numbers on the bottom were slightly different? What if it was a really, really small mass moving relatively quickly? Like an electron. So if we take an electron and a hydrogen atom, we do the same calculation, I get 3 times 10 to the minus 10 meters. This is barely detectable. We can detect that. Not easily, not, probably not in your kitchen, but on Earth, in our high-tech science labs, we can. Matter of fact, that's about 6 times bigger than the size of the atom that it's in. So again, this is something detectable. This moves into quantum mechanics. Have a fantabulous day, and thank you for your time.